Now I will discuss some problems arising in the regression model with cross-section data. In Lesson 5.1, we will deal with heteroscedastic and non-normal errors. This is the index. We will start by a short introduction. Then we will discuss the causes and consequences of non-normality. Then we will do the same for heteroskedasticity. We will last present a practical case, and as always, we will do some highlights, reviewing the main points of this lesson. This lesson discusses non-compliance with two seemingly unrelated general linear model assumptions: homoskedasticity, that is, the errors have constant variance, and normality, which is, the errors are distributed like a normal variable. We will discuss these two problems simultaneously for two reasons. First of all, their consequences are similar, and second, they overlap somehow because, first, there are non-normal distributions which produce heteroskedastic data, for example, the log-normal distribution. Second, when we are testing for normality with heteroskedastic data, the null is often rejected because the test assumes that the data is homoskedastic. And third, outliers may create an appearance of non-normality and/or heteroskedasticity. We will discuss this issue in the next lesson. To describe these points, we will always follow the same schema. First of all, we will explain when do these problems typically arise. Second, we will discuss their consequences, which are very similar, as you will see. And last, we will explain which tools do we have to detect them and how can we solve them. Even if the errors in the model are non-normal or heteroskedastic, OLS point estimates will be pretty good, as they continue being unbiased and consistent. On the other hand, you will lose some standard OLS properties. First of all, your estimates will not be efficient in the strict maximum likelihood sense. This means that when you comply with all the model assumptions, OLS estimates are maximum likelihood, and therefore they are the optimal, in the sense of minimal variance, unbiased estimates. However, if you lose normality, your estimates will only be Gauss-Markov efficient, meaning that they will be the optimal linear unbiased estimator. Last, if you have heteroskedastic errors, your estimates will not be efficient in any sense. The second property that you lose is the standard results for calculating testing, hypothesis testing. If you apply the standard OLS formulae to hypothesis testing, you will compute p-values for the null hypothesis that will be biased. They will be larger or smaller than the correct ones. And last, the standard confidence intervals that you can compute will not be valid. This happens because these three results, efficiency, standard hypothesis testing, and the standard confidence interval, assume that the errors are independent draws from a homoskedastic normal distribution. However, when you prove unbiasedness and consistency of the OLS estimator, you are not using these assumptions. Last, heteroskedasticity has two specific consequences. First of all, the variance of your errors changes. This means that when you will be forecasting, using your model to compute forecasts, sometimes your forecast will be very good and sometimes your forecast will be very bad because the variance of the error will change. Second, if the errors are heteroskedastic, you expect YT to be heteroskedastic too. And this happens because the distribution of YT conditional to the true values of xt, this notation means the conditional distribution of YT, will be normal, if you continue holding the normality assumption, with this mean and this variance, which is the same variance of the error. Now we will discuss the issue of non-normality. When working with economic data, the main cause for non-normality is that the variable that you are modeling is non-negative, with values both close and far from zero. In this case, strict normality of the data is impossible, so probably the model errors will be non-normal too. If the errors are non-normal, you will have unbiasedness of point estimates, efficiency in the Gauss-Markov sense, and consistency. On the other hand, standard hypothesis testing and confidence intervals are not valid. In the figure, we have an example for a variable that complies with this case, the case of non-normality because non-negativity. What you have here is the histogram of the variable wage, which is included in the Woolrich Beauty dataset. This is a sample of wages in US dollars per hour for USA workers. What you have here is the distribution of wages over the sample. As you see, it is defined positive. You get money for working, you don't pay for that. And what you have overlapped in the thin line is the shape of a perfect normal distribution with the same sample mean and the same sample variance. As you see, the shapes of both distributions is very different. What you have here above, and we will speak about this later, is a test for the null hypothesis of non-normality. The statistic is very large, and the figure in brackets is the p-value, so you are strongly rejecting the null of normality. Sometimes non-normality is a structural feature of the data. For example, consider the figure representing this time series. These are the daily returns of IBEX 35. As you can see, there are periods in which this series has lots of volatility. The stock exchange is quiet, and there are other periods in which the observations are closer to the mean. If you compute the histogram for this time series, you see that there is an excess kurtosis, meaning that there are more observations close to the mean than the normal distribution predicts. This corresponds to these periods. And also, there are values very far from the mean, which arise in these periods of large volatility, these clusters of large volatility. In this case, the excess kurtosis, and therefore the non-normality, is due to the intrinsic heteroskedasticity of the time series. And this is a very common feature of financial data. Another frequent cause for the rejection of the normality assumption is the presence of outliers in the sample, which creates an appearance of non-normality and sometimes even of heteroskedasticity. On the other hand, as we will see in the next lesson, outliers can be a problem by themselves, as they can distort the estimates. In this case, they are termed influential observations. The figures show the distribution of the number of days of gestation in the dataset maternal smoking of Gretel and its relationship with the child birth weight. As you can see, there are 3 data points, which are probably erroneous, corresponding to children with a very small period of gestation and in some cases a very large birth weight. These values probably are erroneous and they create a left skewed distribution which would yield to a rejection of the hypothesis of normality. How can we test for normality of the data or the model errors? Most normality tests are variants of the Jarque-Beer statistic, which null is that the skewness of the data is 0 and the kurtosis or pointedness is 3. These are the 2 defining values of the normal distribution. It builds on the corresponding sample moments. This is the coefficient of symmetry, and this is the coefficient of kurtosis. These are the 3rd and 4th order moments for the centered values of the variable. In this case, we are denoting the variable as x. Both sample moments are combined into the Jarque-Beer statistic. Jarque-Beer statistic is n times the coefficient of symmetry squared divided by 6 and the coefficient of kurtosis minus 3 squared divided by 24. If the data is normal, this statistic will be small because the true value of this moment should be 0 and the true value of the numerator of this expression should be 0 too. In practice, under the null of normality, this statistic will be distributed as a chi-squared with 2 degrees of freedom. So a large value of the statistic leads to the rejection of the null. Typically, you consider that the sample is normal if the Jarque-Beer statistic is below 6. If it is over 6, you typically reject the null with a 95% confidence. Now, let's talk about the treatment. The most appropriate treatment for non-normality depends on the cause. Specifically, in the case of non-negative data, the log transform often induces normality. In the case of heteroskedasticity, okay, we need to deal with the heteroskedasticity. So non-normality may be a derived problem. And in the case of outliers, the best option consists in detecting them and deleting them. Now, let's talk about heteroskedasticity.
There are many variables, mainly financial time series measured with high frequency, which display periods of high and low volatility. In this case, we have the daily percent returns of IBEX 35, a time series that I showed you before. Here you have a cluster of observation with high volatility, another cluster of high volatility, another one. And there are also periods of low volatility, here and here, for example. This type of heteroskedasticity is easily detected by means of a time series plot. When we are working with low frequency time series, that is, a variable which is recorded once per month, once per quarter, or once per year, dispersion often depends on the level of the series. In the figure, we see the monthly number of international airline passengers. This time series is trending as its level moves up. As the series goes up, the variability of it increases. This situation can be easily detected using, again, a standard time series plot, such as the one shown here. In cross-section data, heteroskedasticity often arises when the sample combines spatial units of different size. I refer to different families, firms, and countries. For example, in this XY plot, you have the GDP of a sample of countries and the public spending in health. As you see, there are small countries with a small public expenditure, and here you have the United States, Japan, and Germany. It is clear that it is very easy to model this data, which is close to the origin, and will be very difficult to capture the data of larger units. If you plot GDP against the residual of this regression, you will see that the variability of the residuals increases with GDP. Therefore, plotting the residuals by themselves or against the regressors of the model is an effective detection tool in this case.
Formal heteroskedasticity tests build on the fact that OLS estimates are unbiased. A powerful test for heteroskedasticity is the white statistic. In it, we test the null of homoskedasticity against the alternative that the variance of the error changes due to an unknown relationship between the errors and their regressors. White statistic is computing building on an auxiliary regression of squared OLS residuals against a constant term, the model regressors, its squares, and its second-order cross products. For large sample, the null can be tested with n times the r squared of this statistic, which, under the null of homoskedasticity, is distributed like a chi-square with r degrees of freedom. N is the number of residuals in the auxiliary regression. The r squared is the determination coefficient of the auxiliary regression, and r is the number of explanatory variables in the regression, excluding the constant term. For example, if we have a main model like this, we want to test the null that epsilon t has homoskedastic errors, we would compute the residuals, we would square them, and then regress against a constant term, the same variables, the squares, and the only cross product. The value of r will be, in this case, 5.
Now we are going to discuss how to tackle the problem of a regression model with errors which are heteroskedastic. There are two main treatments to deal with this situation. First, transforming the data, and second, applying an alternative method of estimation which is known as generalized least squares, or GLS, which ultimately is also a data transformation. The most common transformation to deal with heteroskedasticity is the logarithm. Here you have again the airline passengers data, and here you have the corresponding logs. The log transformation reduces the difference in a scale, so the large difference here and the small difference here become very close to each other after the log transformation. This treatment is often useful when working with low-frequency time series. The log transformation is also useful in statistics because it induces linearity in the model and normality in the data. Finally, it is also useful to solve the heteroskedasticity of dwarfs and giants, that is, the one which is due to the presence of units which are large and small in the sample. In the practical case, we will show how this happens. Consider now a standard regression model, like this, in which the error variance can be written like this, so that we have a fixed factor, sigma squared, multiplied by a variable, gamma sub t, which is raised to the squared power. I have done this just to visualize the fact that the variance must be positive. In this situation, the OLS estimate for the transformer model, this transformed model, in which I divided each variable by gamma sub t, that is the square root of the varying factor of the variance of the error. In this model, the error will have a constant variance. So the OLS estimates will have the standard properties, and you will be able to apply the standard hypothesis testing with no problem at all. Therefore, we can see GLS as OLS applied after partially standardizing the error model. A common procedure is to estimate this time-varying part of the error variance by using the values fitted by the Watts test regression. This procedure is the one implemented in Gretel. If you have a large sample, you can be comfortable with your OLS estimates, even if you have non-normal or heteroscedastic errors, because they are unbiased and consistent. In this situation, you can consider an alternative treatment for heteroskedasticity, which is using robust standard errors. Here you have a Gretel window to specify a regression model, and if you click here, what you will do is estimating the OLS estimates for the parameters of the explanatory variables, but you will compute the standard errors in an alternative way. The inference that you will do using these robust standard errors will be valid even if your errors are non-normal or heteroskedastic. What we need to do now is to develop a practical case for heteroskedasticity and then provide some highlights for the whole lesson. The practical case is also in video and you can download it in an alternative file. And that's all that I wanted to tell you in the class of today. Thank you so much for your attention. Good night and good luck.